right, hello everybody, and welcome to the ASIC Virtual Fall Series Session 2. My name is Naomi Zimmerman. I'm a professor in mechanical engineering at the University of British Columbia, here to talk to you about our work on applying low-cost sensors to calculate fleet-based vehicle emission factors. And while I am presenting the work, this is really the work of my master's student, Bingxi Liu, who just graduated. So before we talk about specifics of this study, I want to give you a little bit of context about vehicle emission factors and why we might want to measure them. So an emission factor is essentially just our emissions normalized by the activity that causes them. So we could think about expressing our emissions per unit power, or emissions per distance traveled, or emissions per kilogram of fuel burned. And these are really useful because emission factors are actually often our inputs into our emissions models and our emissions inventories. So these numbers are really critical when we're forecasting or trying to make predictions of emissions in specific areas. But there are some challenges around getting accurate emission factors. One is that there is a lot of things that cause variability in emissions. So, there is a question mark of our models always using representative numbers, because there are things like the effects of operating conditions, environmental conditions, the fuel type, the vehicle class, just to name a few. And also that rapid technological change in vehicles can happen as regulations change. And we often have to play catch up in terms of updating our emissions inventories when technologies are changing. And that's also a challenge because running the experiments typically done to calculate emission factors can be quite expensive, either in terms of just dollar amount or also in terms of time. So we can use things like expensive remote sensing systems or dynamometer studies, but they all incur a fair amount of cost. So just to briefly overview some of the emission factor measurement approaches, we can typically either measure emissions using laboratory or on-road testing approaches at either the vehicle level, which is where we use something like a controlled engine or chassis dynamometer or a portable emissions monitoring system, or at the fleet level using something like roadside remote sensing or a tunnel study. But all of these approaches have challenges in either the cost or number of vehicles tested or operating conditions that are captured at the site. That's specifically true in terms of remote sensing and tunnel studies. And so the question here that Bingxi had been working on, that I've been thinking about, is what about low-cost sensors? Could these be a possible alternative to that near road or roadside remote sensing of emissions? And the advantage of this is you could deploy these at hundreds of locations, so you'd be able to capture more vehicles and a more broad range of vehicle operating conditions, and potentially have millions of plumes for fleet analysis. But the big question mark here is, are low-cost sensors even capable of such measurement given signal-to-noise challenges? And so that's what we thought about addressing. So I'll give you an overview in terms of the tool that was used to look at this question, and that's the Real-Time Affordable Multi-Pollutant Monitor, or the RAMP, which you'll probably be hearing about or have heard about in other sessions. It incorporates some pretty popular commercially available low-cost sensor packages, such as the AlphaSense sensors for gases, and also the Plan Tower sensor for PM 2.5, which of course is in the ever popular purple air sensor. And here on the right, you're seeing a picture of our RAMP sensors co-located at the Metro Vancouver station at Clark Drive, which is the intersection of, or a major intersection with lots and lots of traffic, right beside a truck route, so lots of vehicles. And we used this co-location to actually do the calibration of our data before we began. So highly traffic impacted site to do our calibration for looking at vehicle emission factors. I'm not going to speak about calibration in a ton of detail, other than to mention that it is critical that you do it, and it's very important. And so I would just like to point your attention to a couple papers that influenced the calibration approach that we applied here. This was an original paper that I had published a few years ago about machine learning colocation-based approaches that was further refined based on the work, very nice work of Carl Mallings, who looked at a variety of algorithms that we essentially adopted in this case for the gas phase sensors. And we also adopted Carl's very nice algorithm for correcting the purple air or Plan Tower sensors based on humidity, based on observations that at high relative humidities, these purple air sensors tend to overestimate. And so Carl had developed an empirical algorithm, a parameterized algorithm that we apply in this case based on our own coefficients from the co-location of Metro Vancouver. So the calibration is important and critical. I just don't have time to go into it, but we did do it, and please please do it. And so to get to the study itself, once we had done that co-location and that calibration, we're going to sort of pivot our focus to the University of British Columbia campus, where we did our study in 3 parking garages on campus over the period of 80 days last year. And so we deployed 2 ramps per parking garage across 3 parking garages, so 6 in total. And the purpose of doing this in the parking garages is that it's a highly controlled environment, which also has, singular source, pretty much traffic, and vehicle count data provided by parking services. And the goal was to use this data to calculate calculate emission factors with these low-cost sensors. So here's a picture of an example of the sensor in the garage. So we had one at the entrance exit lanes, and then one in the center of the main corridor, sort of just past the entrance gate. So capturing at multiple locations in each parking garage. And to do the calculation of the emission factors, since we're obviously just measuring concentrations, we applied the carbon balance method to calculating our emission factors. So this involves taking the background subtracted pollutant, in P here, and dividing it by the background subtracted carbon containing species of the in the exhaust, which is primarily CO2 and CO. And so we have that data from the ramp. And then we multiply that by the weight fraction of carbon in the fuel to convert our pollutant data into a kilogram of fuel burn data. And this fraction was assumed to be 0.86 for gasoline, so 0.86 grams of carbon per gram of fuel burned. And so here you end up with an emission factor that's, amount of pollutant per kilogram of fuel. We left it as that in this study, but you could, in theory, also convert this to an estimated emission factor on a distance basis using an assumed fuel economy, which in Vancouver is about 9 liters per 100 kilometers or 26 miles per gallon. So the first thing that we did after to deploy this calculation is, one, we do need to actually do that baseline subtraction. So in this case, we use a rolling spline and local minima across a moving window. Again, not going to go into tons of detail about this, but happy to take questions about it or point you to some references that could be helpful. Needless to say, this is just typical snapshot of a couple hours on one of our days where you can see the CO raw data in blue, and then the estimated baseline in the orange. We then have to do some pre-treatment to the data in terms of identifying plumes and applying some detection limits. So an advantage of using the parking garage data is the availability of real-time vehicle entering and leaving data. And so after removing the background and identifying the plumes, any plumes identified during periods with no vehicle traffic were used to create a cutoff point. And we actually used the 90th percentile of the delta P in concentration above the background during the no vehicle period. And to be considered for emission factor calculation, we then developed 3 criteria. One was that delta P and delta CO2 had to exceed that threshold from the no vehicle period. There then also had to be a matched CO2 and pollutant plume with a bit of tolerance for a gap in the start and end points of those plumes. And there did actually have to be a vehicle entering or leaving the parking garage. So it ended up being redundant. Nothing was eliminated. If it passed 1 and 2, it automatically passed 3. And so here you can see this is just sort of an example of what this sort of looks like. This is just 2 plots. One is delta CO on the top and delta CO2 on the bottom. And Bingshi here has added some red lines to sort of guide your eye to this idea of matching plumes. So it have to be matched CO and CO2 plumes. And he, within his algorithm, had some ability to combine 2 plumes if they were sort of mashed together. And also he's just an example of tolerance of a small gap in terms of the start and the end point of the plumes. And so once we have those delta P and delta CO2, we can work our way through the calculation once it's met all our criteria. And the first thing I want to report is the average emission factors across all our parking garages. And so here, this is a complicated table, but if I point your attention to the box in blue at first, we were reporting sort of for the all data, emission factors of CO, NOx, and PM2.5 in grams per kilogram of fuel. So 18 grams per kilogram of fuel for CO, about 1.8 for NOx, and 0.22 for PM2.5. And there's nothing particularly groundbreaking about these numbers other than the fact that if we compare them to other studies, which is just to the right of that blue box, we can see that our numbers sort of fell within a reasonable range of expected emission factors for these pollutants, where these other studies were using essentially regulatory grade type instrumentation. So for us, that was really heartening that we were able to come up with a similar range of emission factors with our data. The other thing that's really cool, and if we go back to this table, you'll see, hey, you have this morning entering only column. What is that? And the other cool thing about doing this study in the parking garage is that we were actually able to isolate the role of cold start emissions in our calculations. So we know that vehicles entering the garages in the mornings are typically assumed to be warmed up. That's people commuting to campus. And the vehicles leaving the garage in the evening tend to have been sitting all day and have colder engines, and thus may have higher emissions due to the cold start. This isn't a true cold start as defined by regulatory tests, but essentially it's shortly after the vehicle has been turned on is when we are capturing it. And so if we separate our emissions into vehicles coming in the morning and vehicles leaving in the evening, and our emission factors morning entering and evening leaving, we can see in yellow is the morning entering and green is the evening leaving for CO, and now I'm showing it to you for NOx. And there's a couple interesting observations about this. One is Site C. This was our Rose Garden parking garage. It was below ground and had extremely high emissions and very poor ventilation, to the point we couldn't actually consider Site C in the center because there was so much accumulation of pollution that there wasn't actually good dilution of it. So we couldn't isolate plumes very well. And the other is that evening leaving did tend to be higher than morning entering across most locations for both NOx and CO. And the effect was more pronounced from monitors in the center of the parking garages, likely due to being closer to when the vehicle is actually first turned on. These engines do tend to warm up pretty quickly. So in summary, low-cost sensors seem to be a promising tool to assess vehicle emission factors. We hope to scale this idea to other traffic-intensive corridors. Our emissions were in the range of other published studies. And so, by deploying our sensors in the parking garages at UBC, we were also able to look at cold start operation. So I'm out of time, but let's chat about this both in advance or after the talks. Love to hear your input.